Yes, good afternoon, all the students. Let's start our third module today. Yeah, let's start our lecture 1 under module 3 under this machine learning course. Before going to this third module, let's quickly recap once again. This actually helps us to stay tuned with the topics we have learned so far. Okay. So in the second module, we have seen introduction to decision tree learning and how they are represented in the form of roots and in the form of root and child nodes and connected by branches. Okay, and appropriate problems for decision tree learning. What types of problems? The problems with certain characteristics would be best suitable to be learned using decision tree algorithm, right? Such kind of problems, what kind of problems will exactly suit this kind of decision tree learning that we have seen. And the basic decision tree learning algorithm also we have covered, that is ID3 algorithm, and the hypothesis based search in decision tree learning, how it is made by using this ID3 algorithm also has been covered. And the inductive bias in decision tree learnings means the assumptions that the decision tree learning makes in order to arrive at some concise or brief hypothesis or optimal hypothesis that we have seen. And we understood that preferring shorter decision trees by using statistical measurement of information gain is the inductive bias for decision tree learning. And also the issues in decision tree learning we have covered, like overfitting the data, where we may misunderstand it as accuracy is very high, but actually that is overfitting of the data. The machine learning model is learning too much from the data so that it can't generalize well with unseen or new data, right? So how to avoid that overfitting? What are the techniques to avoid that overfitting? We have seen pruning techniques like error reduced pruning and rule post pruning, and also other issues we have discussed, like how to convert continuous valued attributes in order to be in order to make the decision tree learning more comfortable for the model. Okay, all these topics were covered in the last chapter. Now let's move on to this new chapter, artificial neural networks. Okay, this includes little bit of mathematics, so if you stay focused it will be easy for you to understand. But if at all you're not regular to the classes, I can't promise you that you'll understand these concepts, because second chapter is quite easy. You have to compromise little with this third second chapter, decision tree algorithm, right? Yeah, that is quite easy to understand. Now the third chapter, artificial neural networks, is little complex to understand with lots of mathematics, so you should have good concentration during the classes, right? Now in today's class, let's get introduced to this artificial neural networks concept, and what is the biological motivation behind this kind of architecture or this kind of system, that will understand. And what are the representations for this artificial neural networks, how they are actually represented, how to understand each part of this representation. Let's see. And appropriate problems for neural network learning. What are the problems that are most suitable to be conquered with this type of learning, that is artificial neural networks? Okay, now let's start with the introduction. Artificial neural networks provide a general practical method for learning real valued, discrete valued, and vector valued functions. You know what is a real valued function output, right? If you are trying to find out the sale price of a house, or if you are trying to find out the percentage that may be obtained by the student, or if you're trying to forecast the weather, or if you're trying to predict the stock price of shares in the stock market, All these are real valued outputs. Discrete valued outputs you already know, right? Playing tennis, yes or no. Whether your friend has enjoyed the sport, yes or no. Whether a customer is reliable or not. Whether, say, a transaction is fraudulent or not, right? All these are discrete valued attributes. Discrete valued outcomes. And vector valued functions are a series of outputs if you have like an array, right? In that case, we call it as vector valued functions, where you have an array of outputs to be treated as one single output to take some decision, right? Those are called as vector valued functions. They have both, in physics we have learned, right? Vector is which has both magnitude and direction. So these vector valued outcomes will help us to take a decision on the entire set of output values. Okay, that we call as vector valued output functions. Now, algorithms such as backpropagation use gradient descent to tune network parameters to best fit a training set of input-output pairs. I already gave you an example about gradient descent. When a person wants to climb down the mountain, or when a person wants to climb up the mountain, how he takes a decision. He takes a decision by taking his locally available solutions. In that, which is the best optimal solution, in that direction he moves to reach his destination, right? That is called as gradient ascent or gradient descent. Okay, now algorithms such as backpropagation use gradient descent to tune these network parameters. Lots of parameters will be available. How many number of hidden layers should be there? How many number of neurons should be there for each hidden layer? These are all various hyperparameters. Hyperparameters means the parameters which affect the outcome. Okay, so these parameters have to be tuned in order to arrive at a best solution. Say if you're taking k nearest neighbor, in that k is called as the hyperparameter, means how many neighbors to consider in order to assign a particular data point to a cluster. That is called as k nearest neighbor algorithm. Now in that, k is called as hyperparameter. This hyperparameter is not part of the dataset parameter, right? It is used in the algorithm that is used to fit the data set. Parameters or attributes or features in the data set, they are different. They are called as just the parameters, but the parameters you use to make your algorithm best suitable to the data. In order to obtain a best fit of your model to the data, you have to make adjustments in some parameters. Those are called as hyperparameters, right? Or meta parameters, we can call them. Okay, so what kind of tuning you require, that can be explained by using various algorithms under AN. Algorithms such as backpropagation use gradient descent to tune network parameters to best fit a training set of input-output pairs, right? And ANN learning is robust to errors in the training data. Though there is noise in the training data, though there are errors in the training data, still ANN is not quite deviating with such kinds of noise in the data. It is very robust to such kind of errors in the training data and has been successfully applied to problems such as interpreting visual scenes, speech recognition, and learning robot control strategies. Say interpreting visual scenes. And you may have a robot which will interpret the visual scenes based on the scenes that are encountered by the robot. It will try to classify this scene is a friendly scene, or this scene is an academic institution scene. Like that, it will be able to categorize between the scenes it comes across. Okay, in that case, you just understand how many pixels have to be processed at what amount of speed in order to categorize that particular scene very quickly in order to give some result. Or you take an autonomous driving vehicle. Now when it is driving on the road, it comes across lots of traffic, right? And each moment it has to classify the next, it has to classify the situation it is coming across, and it has to take a very optimal decision in order to drive safely without any accidents. Correct? For that, see the speed of processing of the data. Okay, such kind, and also there is lots of noise, right, on the road when it is trying to drive. Lots of noise in the data is encountered. But how to overcome all such deviations in order to take a perfect decision to move forward without encountering any failures or accidents. Okay, that is very important. And in speech recognition has a lot of complexities, right? It may have to decide on the gender of the voice. It may have to decide on the accent. It may have to decide on the language. It may have to decide on the context in which that particular word is being used. I say good means it is a positive sentiment. I say bad means it is a negative sentiment. But if I say not good, but by seeing good itself, it can't say it is a positive sentiment, because I have attached not with good. Not good is equal to actually bad, right? In that case, how to use its experience in order to perform word sense disambiguation. Disambiguation means avoiding the confusion between the usage of words, right? How that is being done, right? That involves lots of complex features. And learning robot control strategies. Robot have to control lots of strategies, right? It has to plan differently at different instances. As I quoted in your initial classes, you can see that Android Kunjappan movie in Netflix. The robo may not be able to understand the emotions of humans. Still, it is not trained to understand the emotions of human, though it performs almost all the tasks as human beings. Now, when you're controlling, when that robot is controlling itself, in what way it has to react to human actions, okay, that has to be deeply studied, and accordingly the models have to be built. Otherwise robots will result in becoming a hazard or danger to the humans. So in this kinds of situations, artificial neural networks will be very useful. You can train them in multiple levels in order to arrive at more accurate predictions. Okay. Now, neural network learning methods provide a robust approach to approximating real valued, discrete valued, and vector valued target functions. Okay. Remember, see here, I'm using the word approximating. It is not accurately predicting, it is just approximating. That is why prediction is always associated with some error. It is not 100% correct all the time. There is always some error associated with the prediction. That is why we call it as approximation. Okay. Now, for problems such as learning to interpret complex real-world sensor data, artificial neural networks are among the most effective learning methods. In order to conquer this kind of complex real-time situations, these artificial neural networks are always, they have proven to be effective. And backpropagation algorithm, which we are going to see in this chapter, has proven successful in many practical problems such as learning to recognize handwritten characters. This requires artificial neural networks. Why? Because each person writes a particular number in 100 different ways, right? Now, in order to make a machine learn from this 100 different ways and making it to predict whether a particular character is a specific number or a letter, that is not a simple task, right? So artificial neural networks will work very well at such kind of problems. Learning to Lots of input data can be given. What all possible variants of writing a particular number or writing a particular letter can be taken, and that can be used as training data to the artificial, which can be given to the artificial neural networks and make it to learn so that it predicts well with the unseen data. When a new numeral is given or when a new letter is given, it should be able to predict what it is in whatever way it is written, by whomever it is written. It should be able to predict that properly, right? For such kind of voluminous tasks, artificial neural networks are the best option. And learning to recognize spoken words. Lots of variations in speaking the words are possible, right? Neutral accent, American accent, Indian accent, and again in India, 29 districts accents, a particular word can be spoken. That is, and they actually do not follow phonetics at all, right? They utter that particular word in their convenient regional slang. That is why lots of input data have to be provided to the artificial neural networks in order to train it to recognize spoken words, right? And learning to recognize faces. This is the most complex task that is being performed by artificial neural networks with good amount of accuracy. Learning to recognize faces. Say if one person's face is given to be trained on, it will have to detect what are the edges, what are the say rounded shapes, what are the places where there is what to say convex shape on the face, concave shape on the face, which areas are bulging out, which areas are going inside. Each and every feature of the human face have to be first detected as attributes, and then many such faces it has to be trained on, and only then it will be able to recognize the faces, right? So lots of training data should be available. When there is lots of training data and when there is sufficient complexity in training the model, then artificial neural networks are the best suitable networks to be trained on. Now, what is the biological motivation behind this artificial neural network? Whenever I say neural, it should ring the bell for you, right? It is related to human brain, because human brain is a composition of lots of hundreds, thousands, lakhs of neurons, and each neuron will communicate with each other neuron in order to send signals. Actually, you should be able to admire the working of your brain, of a human brain, and we should thank God, because no science, actually it is beyond science to understand a human brain, how it functions. Still it is a mystery to many of the scientists how a human brain actually functions, right? That much complexity is involved in the neurons, in the communication of neurons in the human brain. Now, biological learning systems are built of very complex webs of interconnected neurons. Everywhere there are lots of neurons interconnected, and each neuron fires a particular action to the next neuron, and that fires further to another neuron, and that fires, and so on. Up to 100 to 200 or 300 firings of neurons should take place in order to make you feel that your fingertip is itching, right? For that much complex firing of neurons will take place, that much complex communication between the neurons will take place. Say if you are feeling itching sensation here, that will first be triggered in your brain, and neurons will start communicating, and it will immediately send a signal to your left hand in order to make it scratch where it is itching, right? That is a silly simple example what I'm trying to tell you to make you understand about the working of neurons. Or how they say it's such a boon when you're going on the road. When a vehicle comes in front of you, immediately you will process that and you will try to escape from it in order to avoid an accident. Think, if at all in your brain that triggering of neuron doesn't take place, you stand still on the road, though a vehicle approaches you and hits you, you will not be able to move. That happens with many Alzheimer's patients, right? Cognitive impairment happens in their mind where the neurons doesn't communicate properly, and they will not be able to do the minimal tasks on daily activities. They will not be able to understand that they have to go to washroom. They will not be able to understand that they have to swallow what is given into their mouth. That is because the neurons firing doesn't take place properly in the brain. That important is the neurons communication in a human brain, right? I have, I think, deviated a little, but I just wanted to make you understand how important is the firing of neurons or the communication between the neurons in human brain. Right now, artificial neural networks are built out of a densely interconnected set of simple units where each unit takes a number of real valued inputs, possibly the outputs of other units. Means not only inputs from a particular image or photograph. Sometimes within the neural network you may have outputs of other layers as inputs to the current layers, and output of this layer serving as input to other next level of layers, right? In that way the construction of neural networks can be taken place. Artificial neural networks are built out of a densely interconnected set of simple units where each unit takes a number of real valued inputs and produces a single real valued output, which may become the input to other units or which itself can be the output of the entire neural network architecture. Right? Now, to understand better, let us consider a few facts from neurobiology. Let me take you back to this brain example and make you experience more better how these artificial neural networks actually works. The human brain, for example, is estimated to contain a densely interconnected network of approximately 10 power 11 neurons. That is not a simple number, right? 10 power 11 means 11 zeros after 1. 10 power 11 neurons, each connected on average to 10 power 4 other neurons. Means it is totally how many lines of communication? 10 power 11 into 10 power 4. See the volume of structures, neuron communication structures we have in our brain. Now, neuron activity is typically excited or inhibited through connections to other neurons, right? So one neuron is excited, it triggers some action to the next neuron, and it triggers some action to the next neuron, and so on. And this 100 or 200 or 300 steps of triggering doesn't take 1 or 2 hours. It just takes fractions of milliseconds, right? Fractions of nanoseconds. That fast is the communication in a human brain. That's a wonder, right? The fastest neuron switching times are known to be on the order of 10 power minus 3 seconds, quite slow compared to computer switching speeds of 10 power minus 10 seconds. Say some people does multitasking. How do they switch between the tasks? And how, for a single task at least, how those multiple neurons are switching so quickly? When compared to computers, though it is somewhat slower, humans are able to make surprisingly complex decisions surprisingly quickly. As I gave you the example of person walking on the road and he is confronted by a vehicle almost colliding with him, he'll take a quick decision to escape or go to the side of the road. How is it possible? How is it being processed so quickly in the human brain, though it is not as fast as the computer switching speed? That's a miracle, right? Now, the information processing abilities of biological neural systems follow from highly parallel processes operating on representations that are distributed over many neurons. This is the motivation for artificial neural networks. A process doesn't take place in a serial manner. It takes place parallelly. Means different triggering of the neurons happens parallelly in fractions of seconds in order to make a human brain indicate to take some action, right? That is the motivation behind this artificial neural networks. It is not a serial processing of the information. It is parallel processing of the information, simultaneous processing of the information, processing of multiple information at the same time. That is the motivation for artificial neural networks. There are many complexities to biological neural systems that are not modeled by artificial neural networks. There are still lots of complexities. As I said, even science or say famous scientists can't understand the complexities of biological neural systems till now. And there are many such complexities to biological neural systems that are not modeled by artificial neural networks. And I think they can't be modeled by artificial neural networks because it is beyond the reach of science. But still, the basic structure can be made of use. They can be used in building this artificial neural networks. The basic structure is very important for us. The basic idea, the notion behind this biological neural systems will help us to build this artificial neural networks up to some extent possible, which will help us to conquer various complex problems at hand. Okay, and many features of the artificial neural networks are known to be inconsistent with biological systems also. Sometimes, say, you are giving multiple inputs, you are getting a single output. You are giving single input, you are getting multiple outputs. Not single input, but a smaller number of inputs, but you're getting larger number of outputs. This kind of inconsistencies, actually, the human biological neural system doesn't have this kind of artificially, designed neural network architecture. But still, though there is some incompatibility between this natural biological neural system and the artificial neural networks, still the basic idea can be taken in order to model these artificial neural networks, right? Now, what is the representation of how the artificial neural networks are represented? Let's see. A prototypical example of ANN learning is provided by a system called Alvin. Typical means it's like a model, right? We are taking the system called as Alvin, which is automated driving vehicle, how it learns in order to drive safely, how it learns from its current experiences in order to drive safely. Okay, with respect to that Alvin system, let us understand how these neural networks are represented. Because if we take a real example, I think it will be easy for us to understand the concept. Now, it uses a learned artificial neural network in order to steer an autonomous vehicle driving at normal speeds on public highways. Okay, so it uses artificial neural networks in order to steer forward on the public highways. Now, the input to the neural network is a 30 by 32 grid of pixel intensities obtained from a forward pointed camera mounted on the vehicle. So whenever artificial neural network system is trying to process the input data, what kind of data we are actually providing to it? In this case, it is an autonomous driving vehicle. So it gets the input as what is captured by the camera or the sensors that is mounted on the vehicle, right? And that is again in the form of image. It's in the form of not static image, but moving image, right? And image is always represented in the form of pixels, you know that. And wherever with having, if it is a color image, you have the pixel values as RGB. Okay, each taking values from 0 to 256. But if it is a black and white image, then it will be in the form of zeros and ones. Okay, if you take this RGB, if I give 12 and 250 and 100, then I say that that particular pixel is having more green intensity, because for G It is almost nearing to 256. That is how you need to understand. This is in the case of color pixels. But if you have only black and white pixels, then the entire pixel range will be represented by only zeros and ones. Okay, now in this case, let us come back. The input to the neural network is a 30 by 32 grid of pixel intensities obtained from a forward pointed camera mounted on the vehicle. Okay, the camera on the vehicle is trying to capture the images it comes across, and that is transformed into 30 by 32 grid of pixel and given as input to the neural network, which further processes it and immediately guides the vehicle to go in a particular direction. Right? We'll go into depth on this example. You will understand very well on that. Let's proceed slowly. Okay, the network output is the direction in which the vehicle is steered. Correct? That is what I said. It takes the road visuals through the camera, converts it into grid of pixels, gives as input to the artificial neural network. It processes the data and guides the vehicle in order to move in a particular direction. That is the output. Now the artificial neural network is trained to mimic the observed steering commands of a human driving the vehicle for approximately 5 minutes. Okay, it is already trained by a human driving the vehicle for 5 minutes. It has been trained. Now Alvin has used its learned networks. It already learned from the human driving skills to successfully drive at speeds up to 70 miles per hour and for distances of 90 miles on public highways. Okay. Now, from the skill it has obtained from a human driver for 5 minutes, being trained for 5 minutes, now it started driving on a public highway at 70 miles per hour and for distances of around 90 miles. Now let's see how it is actually represented. Say this is the visual that is taken by the sensor cameras or motion capture cameras mounted on the car top. Now, how is it given as input to the neural network? Focus your attention here, this part of the image. Now, this is the road image that it is coming across. So the data, the camera captures this 30 by 32 sensor input retina. This is fixed for a camera, right? So at a time, it can capture 30 by 32 sensor input retina. So it is around 960 pixels. 960 pixels it's capturing at a moment. Now, this data, this entire data, the visual is taken as input, means 960 pixels are given as input to the neural network, which is having 4 hidden units. The intermediate layers in the neural networks are called as hidden layers or hidden units, and it depends on the predictive power based on the amount of accuracy it provides. We can fine tune this, whether it can be 4 hidden layers or it can be just 1 hidden layer or it should be expanded to 10 hidden layers. It depends on how we fine tune the parameters, hyperparameters. Okay, number of hidden layers is a hyperparameter, remember. Now this further processes the input data, 960 pixel data. Remember, this is not only 960 pixel data. Every second it gets 960 pixels of data, and it processes it quickly and gives as output 30 units. Now among those 30 units, it can be guided whether to take a sharp left turn or straight ahead or sharp right turn or anywhere between sharp ahead and sharp right or anywhere ahead between sharp left and straight ahead, like that. Based on which neuron is triggered, that action will be taken by the autonomous vehicle. This is how a neural network works. Now, what is this one? This is how the actual representation of the pixels is done after this layer of processing. Means after four hidden, after the input data is given, see here the input data is taken as these many, around 960 pixels, and they are processed by the four hidden units. These four hidden, during the processing, the data looks like this. The four hidden units data, while it is processing, it looks like this. What are these white pixels? Can you locate these white pixels? Those white pixels are called the positive weights, and the black pixels are called as the negative weights. Positive weights indicate that they add up to the prediction power of the neural network, and negative weights means they are not contributing too much for the prediction. That is how you need to understand. Positive weights always contribute more to the prediction of the output, or more to the prediction of the outcome, and negative weights contribute very less, or they contribute in a negative direction. Okay, means something, if this is negative, then the outcome will be growing. If it is positive, then the positive correlation. If there is a positive correlation, when the positive weight increases, the predictive power also increases. But when there is a negative correlation, when there is negative quotient reducing, then the predictive power increases. Okay, that is called as negative correlation. You need not go into that depth at this stage of understanding neural networks. Do not get confused. Only understand that positive weights are represented by white pixels and negative weights are represented by black pixels. Okay, now this is the stage where the input data is being processed by the hidden layers. Now it will produce an input to the output layers, that is this stage. See, this phase is called as the 30 output units, right? This is the output layer. Now to that output layer, it is giving this particular rectangular box. What is that rectangular box? It indicates 30 units that are given as inputs to the 30 output layers. In this, you can see that on the left hand side, lots of white pixels are there, which indicates that the vehicle have to move in the left hand side direction. If there are white pixels somewhere here, in that case it indicates that the vehicle have to move straight ahead. If there are white pixels on this side, you can say that the vehicle understands that the vehicle have to be moved in right hand side direction. It has to take a sharp right. In that way the pixels are processed. 960 pixels each fraction of second are processed by the 4 hidden units, and these 4 hidden units will give as output this rectangular box, which indicates what is the direction that have to be taken by the vehicle in the next step. Right? This is how the neural network representation is done. This is how the neural networks process the data so quickly that it will help the model to take some important and quick decisions. Now, the network structure of Alvin is typical of many artificial neural networks. Here, the individual units are interconnected in layers that form a direct acyclic graph. Right? Why we call it as acyclic graph? Say these are the input units, these are the hidden layers. They are connected like this, and finally these output some output layer. Right? Now this is the input layer, this is the hidden layer, and this is the output layer. They are connection of neurons, but is there any backward connection again to the beginning? No. In that case, we call it as directed acyclic graph. Acyclic means there is no cycle in the connections. In that case, we call it as acyclic graph. Why we call it as directed? All the input to the all the input is given to the hidden layer, and all the output of hidden layer is given as input to the output layer. This is input layer. Now all the input layers give input to hidden layers. This is the hidden layer, and all the output of hidden layer is taken as input to the output layer, which further gives the result. Now this entire architecture are connected in a directed manner, means input towards output. There is a specific direction, but there is no cycle in the graph. That is why they are called as acyclic graphs. Here the individual units are interconnected in layers that form a directed acyclic graph. Now in general, artificial neural networks can be graphs with many types of structures. They can be acyclic, they can be cyclic, they can be directed, they can be undirected also. Sometimes if the output of output layer is again given as input to the input layer, we call it as cyclic graph. It is not a cyclic graph, it is a cyclic graph because there is again a cycle. The output of the output layer is again further fed as input to the input layer. This is called as back propagation. After some output is given, that is propagated back as input to the input layer. In that case, there is a cycle. We call it as cyclic graph, directed cyclic graph. Now this chapter will focus on the most common and practical artificial neural network approaches which are based on back propagation algorithm. Now learning corresponds to choosing a weight value for each edge in the graph. See, whenever some neural network has an architecture like this, these are called as edges. Okay, now every edge will have a weight. Every edge in the neural network will have a weight. Now learning means what? Learning a neural network means a model is using neural network to learn something, means learning corresponds to choosing a weight value for each edge in the graph. Now for every edge in this graph, a weight will be assigned by learning from the training examples, right? Now although certain types of cycles are allowed, the vast majority of practical applications involve acyclic feed-forward networks only, similar to the network structure used by Alvin. In some cases, though there is back propagation allowed, most of the neural networks use only this feed-forward networks. Feed-forward networks means only the data will be fed from input layer to the output layer. But back propagation algorithm means, back propagation network means, again the output of the output layer will be fed as input to the input layers. That is called as back propagation. Okay, in this chapter we are going to see only back propagation algorithm. Now what are the appropriate problems for neural network learning? ANN learning is well suited to problems in which the training data corresponds to noisy, complex sensor data such as inputs from cameras or microphones. See, when you deploy a CC camera in your community, the input or the input fed into that CC camera is in the form of scenes, visual scenes, right? They can be analyzed by using artificial neural networks. If you take photographs, they can be analyzed by using artificial neural networks. If microphone captures some speech, they can be analyzed using artificial neural networks, right? Because it can deal with complexity. It can deal with the volume of the data you are feeding into it. Larger is the volume of data you feed for learning, better is your prediction through artificial neural networks. You remember that. More and more data you provide to your ANN, more and more better is the prediction. Now the back propagation algorithm is the most commonly used ANN learning technique that we are going to see in later parts of this chapter. Now, what are the appropriate problems for neural network learning? Back propagation algorithm is appropriate for problems with the following characteristics. Instances are represented by many attribute value pairs. Like in decision tree. In decision tree also we have attribute value pairs, right? Humidity normal, humidity high, humidity low, or rain more, rain less. Like that, attribute value pairs. If there are training examples in the form of attribute value pairs, if you take this Alvin system example, all the input is given in the form of pixels. Now for this pixel, this is the intensity. For this pixel, this is the intensity. It is in the form of attribute value pairs, right? For such cases, artificial neural networks are quite suitable. And the target function output may be discrete valued. It can be yes or no, male or female, reliable or not, genuine or not, like that. It can be real valued, forecasting the weather, forecasting the rainfall, forecasting the sale price of a house, or a vector of several real or discrete valued attributes. It can be 10 different directions a vehicle can take. It can be 30 different directions a vehicle can take. It can go left, it can go diagonally left, it can go straight ahead, it can go diagonally right. That way, the target function can be modeled. Now, the training examples may contain errors. It can contain noise. Still, artificial neural networks are robust to that. And fast evaluation of the learned target function may be required. Sorry, let me cover this point first. Long training times are acceptable. Wherever long training times are acceptable, you can take up this artificial neural network models. Because sometimes, say if you want to classify a dog breed, first the neural network have to be trained on lots of such dog photos, so that it will detect the edges and smooth curves and sharp edges, smooth edges. It will try to detect various types of dog images, and based on that learning experience, it will try to predict. A new dog photo is given, it will try to predict the breed, whether it is a Dalmatian or whether it is I don't know, Puggy or something like that. I don't know dog breeds much, but in that way it will be trained on, and it will try to predict with the new dog image. But this training time is very high. Why? Because it has to find out the edges, pixels with each and every part of the image, right? And in order to detect, in order to predict better, it has to be trained on more and more images. For that, it may take hours, and it may even take some days to train the neural networks. So whenever long training times are acceptable for such problems, you can select artificial neural networks, because you are getting good accuracy. You're getting good accuracy in the prediction. Okay. And fast evaluation, fast evaluation of the learned target function may be required. Whenever you want some fast evaluation, say if you're going in an autonomous driving vehicle, and some vehicle is coming right in front of you, and your vehicle is not able to take a decision whether to turn left or right and stays still on the road, what will happen? That is why fast evaluation is required, and artificial neural network is capable of doing that fast evaluation. Though the training time in artificial neural network is more, the evaluation time is quite less. It is very, very less. It will be able to predict something very quickly by evaluating from its experience. Okay. And the ability of humans to understand the learned target function is not important when you don't want what is happening inside the black box. See, in decision tree, you can easily understand if you go towards this condition, if you go in this direction, this condition is satisfied and the outcome is this. If you go in this direction, another condition is checked and you go further, this is your output. It is very clearly interpretable. It is very clearly understandable. In decision tree, what is the hypothesis that the decision tree is following in order to predict something? But in artificial neural networks, it is like a black box. You can't interpret what is happening inside the network, but you arrive at some reliable results. That is why when the ability of humans to understand the learned target function is not very important, you don't want them to understand what is happening inside the black box. In that cases, you can go for artificial neural network models in order to train your machine learning. In order to train your machines. Right? These are the appropriate problems where artificial neural network learning is suitable. Now, in your next class, you're going to learn about perceptrons, representational power of perceptrons, and the perceptron training rule. I request all of you to attend the next class, because at least for this chapter, be regular, because lots of derivations are there, which you miss, you can't understand the later topics. Now quickly answer these questions. What is Alvin? What is Alvin system? We have taken as an example. Students, you are there? Are you there? What is
image capturing?
Image capturing or autonomous driving vehicle? Alvin is autonomous driving vehicle, right? Which will capture images, dynamic images, process the data, and guides the vehicle to move in a particular direction. Alvin system is a autonomous driving vehicle. Are neural networks robust to noise in training data? Yes or no? Are neural networks robust to noise in training data? Students, what is the important feature of neural network? It is robust to noise in training data, right? It is robust to noisy training data. Though there is noise in the training data, still its predictability or its performance doesn't degrade because of that noise. Now, are neural networks more interpretable compared to decision trees? Answer. Speak out something, yes or no. Based on your answer, I'll give you further explanation. Are neural networks more interpretable compared to decision trees? They're understandable compared to decision trees? Tell me. Yes, somebody tried to answer. Neural networks are not interpretable when compared to decision trees. In decision trees, you can interpret what is happening, but in neural networks, it is like a black box. You can't see what is happening inside, how the processing is taking place. That is why when human interpretability is not an issue, in that case, only you have to select neural networks, right? We'll stop the class here. Any doubts in this? Students? Okay, we'll meet in the next class.